I received requests to solve on camera two problems. One from chapter 18 on work and energy, and the other one chapter 19 on momentum, principle, impulse and momentum. So problem 1820, it's about a rod that is guided along a horizontal slot and a slot that is at 45 degrees. It starts from horizontal position and it's at rest, in a force P of 200 Newton pushes the right end, and we need to find the angular velocity right before theta of the rod becomes 45, so essentially right before the rod aligns with the fully with the inclined slot. So I said we're going to use principle of work and energy combined with conservation of energy, the way we figured out in class that it's possible. So the combined equation, and let me pause because I want to state that equation. Okay, so what I did, this is in Paint, so I combined the equations, and it's the way we're going to use them. So initial kinetic energy plus initial potential energy of gravity and springs plus the work done between initial and final position equals the kinetic energy and the potential energy in the final position. The rod performs a general plane motion. Its kinetic energy is translational kinetic energy of the center of mass plus rotational energy of the rod about the centroid, or we can use instant centers to calculate the total kinetic energy. Again, combination of rotation and translation of the body. So we have the option to use this other equation, 18.7, where kinetic energy is mass moment of inertia of the rod about the centroid, the instant center, the instant center of velocity times omega squared, and the one that we need to find. Okay, so this is the problem. Let me bring up the problem the way I solved it. Okay, so I have the drawing the way it's shown in the book, with an angle theta other than 45 and other than 0. But again, the rod is originally horizontal, and at the end it will be a line with the incline. I'm going to take the datum for potential energy at the x-axis, y equals 0. What I did, I calculated, so clearly I'm going to use the kinetic energy as translational kinetic energy plus rotational energy about the centroid. So the centroidal center of mass is at the middle G. Centroidal mass moment of inertia is, from the back of the book, 1/12 ml squared. Mass is given for the rod is 15 kilograms. Length is 600 millimeters or 0.6 meters. Okay, so I have IG, and I'm stating the work energy equation. So initial kinetic energy, initial potential energy plus the work of force P between initial and final position equals final kinetic energy and final potential energy. Since the rod is aligned with the datum line, potential energy is 0. It starts from rest. The kinetic energy initially is 0, so these two are 0. I said datum is shown and starts from rest. So what I have to the left is only P, this constant force, times the amount of travel of its point of application, and because the rod is originally horizontal and then goes sloped, so the travel will be exactly the length of the rod. So S here, the amount of travel or displacement of point of application of force P is 0.6 meters. So U from 1 to 2 is P times S, which is the length of the S is the length of the rod. Okay. To the right we have kinetic energy of the looks like I missed something. So let's see. I think I missed the V2 part altogether. So, and we'll correct that. So this is equal to, I said, translational kinetic energy, and then rotational kinetic energy, and then yes, I did forgot to add V2. Let me pause again. Okay, so mistake corrected. Excuse me. So I was missing the I was missing the potential energy term. Apologize for the sneezing. I had the elevation of the center mass in the final position calculated. We have the angle 45. This is half the length, that is 0.3 meters. So it will be 0.3 meters sine of 45 degrees. That's 0.15 times square root of 2. Okay, so again, the work of the force P, it's P times displacement of B, which is exactly length of 0.6 length of the rod. I label it as here, equals translational kinetic energy of the center mass, rotational kinetic energy of the rod about its centroid, plus potential energy in the final position. So it'll be M mass of the rod times the elevation of its center of mass, which we calculated earlier. Okay, so let's see how can we, so this is what we need to find, omega. How can we express velocity of the center of mass as function of omega? And we're looking at this figure here. It's right before the rod aligns with the incline. It still had point B, it's still moving horizontally. Point A, it's already moving on the incline. We can find the centroid by drawing the perpendicular to the oblique line, and then drawing the perpendicular to, essentially perpendicular to the velocity of B, which we know their direction, and velocity of A know their direction. So we have a right angle triangle with a 45-degree angle. So this definitely has to be 45. It means it's an isosceles triangle. It means that the distance from A to the instant center is same from A to B, that is 0.6 meters. So we need to calculate in order to find the velocity of the center of mass. We need to calculate the let me use blue. I'm going to even show the velocity. So I'm drawing the velocity like a perpendicular vector to the line from instant center to the center of mass. So this is the velocity of the center of mass. Okay. Again, 0.3 was meters, was just half of this. Okay, so I'm going to state the velocity of the center of mass as omega of the rod times the distance from the instant center to the center of mass. How do you get it? We have a right angle triangle here. One side is 0.6, the other one is 0.3. The hypotenuse is going to be, that is ICG, is going to be 0.6 squared plus 0.3 squared square rooted. So here you have it, and so it's 0.6708. Okay, so again, the in the energy equation, the velocity of the center of mass is distance from the instant center to G multiplied by omega, and I'm now having just omega as the unknown. Okay, so I'm putting numbers now. 200, the force displacement 0.6 equals 1/2 mass 15 kilograms, and then velocity of g is 0.6708 times omega squared, and then plus the rotational kinetic energy about the center of mass, the centroid, 1/2 mass moment of inertia of the rod about the center. We have it. Calculate 0.45 kilogram meter squared times omega squared. So I have an equation in omega squared, and of course there's the one that I was missing. So the final potential energy mass 15 kilograms times the height from the datum to where the center of mass of the rod is in the final position. Okay, so this piece 15 times 0.15 times square root of 2 is 2.25 square root of 2. Okay, so this left hand side is 120 minus 2.25 square root of 2 makes 116.818 equals, this happens to be, if you keep all the decimal, if you square it, it's 0.45. So you have 1/2 15 times 0.45 times omega squared plus 1/2 0.45 times omega squared. Some coincidence here. So when multiplies omega squared, it's 3.6. The free terms are 116.818. Final answer omega is 5.696 radians per second. Okay, so this was the first problem. Let me pause and bring up the... Okay, so the other request was for me to go over problem 1925. So it's from chapter 19 on momentum, impulse momentum for rigid bodies in 2 dimensions. And so what is the problem about? We have a flywheel. We're given the for the flywheel the weight, flywheel at A, the weight or A, and a radius of gyration about its axis of rotation. And these are symmetric bodies. The centroid is on the axis of rotation. And it derives via a pulley. There is no slip. A disc of 500 pounds, rather 50 pounds. So we have this time we can calculate mass moment of inertia by just using the equation from the back of the book. So for a thin circular disc or a cylinder, same equations. For the z-axis, moment of inertia is 1/2 mr squared. Okay, so we have the weights. We can get the mass in slugs by dividing by accelerated to gravity, 32.2 feet per second squared. And what do we have? We have the system originally at rest, and there's a moment applied to the flywheel. It's shown counterclockwise, and moment is function of time, 50 times t pound-foot. Okay, so we need to find the time it takes for the it said the disk. Oh man. The disk to attain an angular velocity of 60 radians per second. I solved the problem for the disk. Oh my, has been a long semester. For the actual flywheel getting to 60 radians per second, but we can fix it. So here is the equations to use. We have we're going to apply the principal angular impulse and angular momentum, and will be a systems of 2 rotating bodies, although we can calculate an equivalent mass moment of inertia, but we're going to use this equation. So initial angular momentum plus the impulse of the moment between 0 and t that we need to find equals final angular momentum, and the angular momentum will be of the two rotating bodies. Okay. So one thing is that the disk will, because it has 9-inch radius versus a flywheel 6-inch radius, so the disk is going to rotate slower. You can, and it's somewhere in the book explained. So the tangential velocity of the disk of the flywheel and tangential velocity of the disk is the same, and it's that of the velocity of the belt, because there is no slip. And you just say omega of the flywheel. You can say omega A, although I use omega A times RA equals V, and V is also equal omega B times RB. Alright, this is RA and RB. So you eliminate V between the two and you get omega A over omega. This is like very basic mechanical engineering things to know. So omega A over omega B is going to be the inverse of radii, will be RB over RA. Every, not even engineers, every person that's involved with mechanical engineering know that if you go from a small diameter to a larger diameter, there's a reduction in the transmission ratios inverse to the radii. So you know you are going to get an omega B that is less, so make sure that you use RA and RB such that by solving for omega B you get a smaller value than the input. Okay, anyway, the reasons are those explained. Velocity of the belt is the same with the tangential velocity of the disk, of the flywheel and end of the disk. And again, we're going to use this equation. So let me bring up the problem, the way I solve it. Let's say yes. And I use the notation omega, and I assumed in my solution that we are going to calculate the time until omega gets to 60 radians per second, not omega b, but that can be corrected. So firstly, I calculated the mass moments of inertia of the flywheel and of the disk. The flywheel, we had the weight and the radius of gyration, so 30 pounds over 32.2, and then in order to have slug feet, we converted inches to feet by divided by 12, and so 6 inches and 9 inches. Why put 4 here? Let me pause. Sorry, there was no mistake. So this is the 4 inches is the radius of gyration. We're not going to use the radius of the flywheel. It's radius of gyration. There is some mass redistribution. This is not a perfect disc. Probably has a web and a thicker rim. Okay, as for the disc, a known formula: a thin disc or a solid cylinder about its longitudinal axis, mass in slugs times the radius squared, but again in feet. So we have the two mass moment of inertia about their axis of rotation for the flywheel and for the disc. And then the equation that I used earlier, stated here: transmission ratio 2/3. It's input omega A or omega over omega B. So principle of impulse and momentum. I can go back to so this is the equation. Initially at rest, it means that this part is 0. We have just one moment, so it'll be an integral from 0 to t of m dt. And to the right we have two angular momenta, one for the flywheel, the other one for the disk. Okay, so this is what you have here. The principle of, can I change it? Not anymore. Okay, principle, impulse, and momentum. So the moment is function of time, 50t, pound foot. Okay, I thought I got it to where it was inches, so we should have converted to same units, feet, but it's already given in pound foot. Oh, luckily. So the impulse of the moment m, integral from 0 to t, and what I did, I factored omega and I assumed that to be 60. Should have explicit rather omega as function of omega b and made that equal 60, but no harm done. I can stop this or pause it. Okay, so I'm back. I fixed my equations. The principal, impulse, and momentum equation, mass moment of inertia of the flywheel times the omega of the flywheel plus mass moment of inertia of the disk times the omega of the disk. And since omega b is the one that we need to get it to 60 radians per second, we are going to substitute omega b times the transmission ratio, inverse transmission ratio, that is 3/2. 3/2 is 6, rather 9/6. 9/6. So we are the left hand side, it's easy. Integral from 0 to t of 50t dt, that's 50t squared over 2. And then to the right we calculated IA and IB, and of course this is no longer correct, so let me pause again and continue fixing the equation. Okay, so more patching of the solution that I photographed here. Alright, so again, all started because I thought it's the input that has to be 60 radians per second. Actually, it was the output, the slower moving disk. So the answer that I got was, as expected, was a bigger number. Longer time. Okay, so we've got the left hand side, this integral 50 t squared over 2. This is essentially 25 times t squared. What's to the right is mass moment of inertia of the flywheel times 3/2 is the inverse transmission ratio, plus mass moment of inertia of the disk, all times 60 because this is what we want, the omega b that multiplies the two want to be. So this whole piece here is 35.517, and are going to divide it by 25. Again, 50 divided by 2 is 25, and then take the square root. So answer is in 1 second, 1.1919 seconds, the input flywheel will get to rather omega b, omega b will get to 60 radians per second. Okay, so this was it, 25 minutes of recording. I hope it will be useful to you folks, and good luck with the final.